Good morning, everyone, and welcome to our first STEM session of this week, which is going to be our Zap, Crackle and Pop with Marty Jopson. And Marty has been making science television for over 20 years, working in many roles from researcher to executive. His career has actually spanned over 10 years, and he has been a science reporter on the BBC One flagship programme, The One Show. He has also been on regional, national and international series, such as Intervention Nation on BBC One. He's also been in the House of the 50s Built on C4, and then Food Factory, which I'm sure many of you have seen on BBC One, and also The Brainiac on Sky One. So I hope you guys are ready for a fun-filled session with Marty, and welcome to our first West Suffolk College STEMtastic event. Marty, I think we are over to you.
Okay, brilliant. Am I turned on? Yes, I'm all plugged in and turned on. Good, good, good. There, just had a little moment where I had to rush out, but I'm back. Here I am. Excellent. So, right, thank you very much. Okay, you hand over to me. I shall start off. Right, where are we? I'll just get that positioned right. And if anybody's got any questions, do put them in the Q&A. Okay, so hello, everybody. Right, my name's Marty Jopson. I am a science communicator, and I am here to talk to you today about some of the weird things I do. Now, I've spent a lot of time doing all sorts of crazy, weird, strange, and fantastic, quite frankly, things all over the country, doing a lot of telly, as you've just been explained. But along the way, I've also spent a lot of time, and quite why is a long story, messing around with high voltage equipment, and I've become a bit of a sort of a thing that I do, and I've built a whole load of high voltage pieces of equipment. So this is my workshop, and these are some of my high voltage bits of kit. So hopefully we're going to be able to show you some stuff. So let's start by making some high voltages. Okay, let's make a high voltage. Very simple. Here we go. Are you ready? There you go. High voltage. Simple as that. That's all you need to make a high voltage. I probably created something, there's about probably 1,000 volts of voltage or potential difference sitting on this wand here, this piece of polypropylene rod. And all you need to do is take two materials and rub them together like that. And that is enough to create a high voltage on something like this. And in fact, it's very simple, because what's happening is if you have any two materials and you place them together, you don't even need to rub them. All you need to do is place them together and then take them apart. What will happen is some of the electrons that are whizzing around in the atoms that everything is made of will be transferred from one to the other. Just keeping an eye on what's going on there on my computer screen. And in fact, in this case, the nylon, which is what this is a piece of nylon from Hobbycraft, and this is a piece of, as I say, polypropylene plastic piping from B&Q. And if I rub them together, I transfer electrons from the nylon to the polypropylene, because the nylon's good at giving up electrons, and the polypropylene is less good at giving up electrons. It's more good at receiving electrons. Now, this is my favorite demo because I find it quite surprising. But basically, if you create, and can you hear that? You might be able to hear a sort of a sparkly thing going on. I remember when my kids were at primary school, they always used to have that, you know, they'd have those horrible sort of those off, we pull them off, and they would create a huge amount of sparks for the same reason. But anyway, you generate a whole pile of static electricity like that, and I can hear it crackling away like that. And then you just discharge your hand, pick up a piece of silver foil, and there you go. And it floats in the air. The floating orb. It's like magic. I have to bring it down so that you can actually see it in camera. So the difficulty here is keeping it in shot at the same time as me being in shot. This is the trick, and you can see, hopefully you can see that, because I haven't got a clue what you're seeing. Oh, it's gone out of shot. There you go. There. You can see that it's floating around in shot. There's nothing holding it in the air other than, and I can steer it around, other than the static electricity. And you can sort of bring it, I try it right up in the air, let it go, and then I can pick it up again like this. It's very simple. And this is just a piece of It's actually space blanket that I use, which is basically tin foil or sort of aluminium foil coated onto a plastic sheet. There you go. Now, the first guy to discover this was a guy called Thales of Miletus, way back in 600 BC. And he discovered this using cats and amber. He thought it was something to do with cats, apparently, and the amber. And whether or not this is true, this is one of these pieces of history of science where you're never quite sure whether these things are absolutely true, because, you know, 600 BC, that's 2,500 years ago. That's a long time. But what we do know is that the word amber in Greek is electros. So we know that that's where our word electricity comes from, and all of the derived things like electrons and stuff like that. So it's dead easy to make high voltages. What's harder is to do something with them. Now, let me switch to a different camera so I'm a bit closer up. Let me pull up this window here as well, just to see what's going on there. I'm just checking the chat. Okay, that's nothing to do with me. Good, right. If you've got any questions, by the way, I will try and answer them as we go along. All you have to do is post them in the Q&A. You know the form, Q&A at the bottom. Just type in your questions, and anything that I see on the screen there, I will try and answer as we go. Or if we have time at the end, it's unlikely because I tend to waffle on, I can answer them at the end. Alfie asking me, how is it actually formed by the pole versus the cloth? I'm going to come on to that a little bit later, Alfie. So we will come on to that, because the thing is, what happened next in the history of science? Well, it took about 2,000 years to about 1663 to be precise. There was a guy called Otto von Guericke, who was a German. He's a bit of a hero of mine, actually. Otto von Guericke invents a machine to do the cat hassling. So rather than having to have a cat and a piece of amber and kind of hassle the cat with the amber, all you had to do was wind the machine and you would create static electricity. It was a very simple machine. It just spun a ball of sulfur, which does roughly the same thing. And that would generate all the static electricity. Now, we've gone on to make more static electricity generating machines. And the one that you're probably familiar with is one called a Van de Graaff generator. It was invented by 1929 by a guy called Robert Van de Graaff. It's fairly straightforward. Anyway, so Robert invents the Van de Graaff generator. Now, I have built a Van de Graaff generator. I call it the Beast. Here it is. My cloth here. Here is the Beast. I shall reveal the Beast. Da, 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 da. The Beast is called the Beast, not because it's beastly in size, although, and I'll put myself in the corner here, not because it's beastly in size, I mean, it is beastly in size, but because it's a beast to make it work reliably. It's actually really difficult to make it work. And unfortunately, I've positioned that camera so that it's right over the top of there. So I'll get rid of my little picture-in-picture and you'll just have to live with me over here. So the obvious thing to do when you've got a big static electricity machine is to charge it up and make some big sparks. So, and it's very simple. This machine works in a very simple way. Essentially, what you have is you are just replicating this action. Okay, you're replicating exactly what I was doing before. And to answer your question, Alfie, all I'm doing is I am literally rubbing electrons from here onto here. So as I do that, the electrons are more welcome, as it were, on this piece of plastic than they are on this piece of plastic, because nylon, it's plastic. So they transfer across. Now, there is a thing called the Triboelectric Series, right? And the Triboelectric Series just lists a whole load of materials and how easy they are relative to the other materials at giving up electrons. Okay, so the materials at the bottom give up electrons very easily, and the materials at the top receive electrons. And what we have here in the Van de Graaff generator, at the bottom, there is a piece of acrylic. And the acrylic is very good at giving away electrons. There is a big rubber band, basically. It's latex, it's artificial latex. And latex is sort of somewhere in the middle of the Triboelectric series. So it sits in the middle. So the acrylic gives up electrons to the rubber band, and then the rubber band carries them up to the top. And then at the top, there's another roller made of a different material called polytetrafluoroethene, or PTFE. It's just a type of plastic. And that plastic is very good at receiving electrons. It's even better at receiving electrons than the rubber band. So now the electrons move onto the PTFE, and then they get taken up onto the big ball at the top. So let's show you a big spark. Now, there are a few problems with this, and what I'm going to do is I'm just going to twist around this, because this is actually the best camera to see this on. All right. Going to try and show you a big spark on this. But well, let me show you what happens, and you'll see what the problem is. Okay, you ready? Okay, I've lost power for some reason. Oh, that's because that's gone to there. Okay, there she goes. Right, she's powering up, powering up, powering up. I'm ready. Here we go. 3, 2, 1, pow. And you didn't see a spark, did you? I heard a spark. You maybe heard the spark. And the spark is happening at about 15 centimeters of distance. Right? And here's the problem. And this is a massive problem with static electricity I have discovered in the last few months doing this. The big problem with static electricity is because when you create a big spark, you also create what's known as an electromagnetic pulse. And that regularly knocks out cameras. In fact, it usually knocks out pretty much all cameras I've tried, even quite really expensive kind of, you know, single lens reflex cameras. It kills the camera momentarily and you don't see anything. Okay. And because you don't see anything, because the camera goes dead, you don't see the spark. And the other problem is, even if it doesn't do that, the spark lasts for such a short period of time that it quite often doesn't appear in the camera feed, because the camera is actually only looking at 30 images a second. So actually, if you think of a second and you're looking at an image and then a gap and then an image and then a gap and then an image and then a gap and then an image and then a gap, and there's 30 of those frames a second and 30 of those gaps a second, that means that there's a good chance the spark falls in the gap between the images, so you don't see the spark. So I can't actually show you a spark, but what I can show you is the effect of a spark. So let me just come back here and check. What does the beast do? Indeed, what does the beast do? We've shown it makes very big sparks. So you might have one of these at school, a Van de Graaff generator, but it'll be like this big. Now this machine will create enough static electricity to make, at the moment it's running there, so that's, sorry, just do the maths. It's about 400,000 volts at the moment, 400,000 volts. The obvious thing to do, let's charge something up to 400,000 volts. The obvious thing to do is to charge me up. I'd like to get a volunteer to do this. There's no volunteers. So what I'm doing is I'm standing on a little stool. Okay, it's just a plastic stool. Here it is. Okay, from IKEA. And that will insulate me from Earth, because I don't want to be Earth. I don't want the electricity to have any way of getting to Earth, and it will therefore, the electrons that pile up on here should just build up on me. So what I'm going to do is I'm going to use my plastic wand as my turning on and off device. I'm going to turn on, and then hopefully I will start to charge up with hundreds of thousands of volts of electricity. So here we go. And I'll put both hands on like that. I can feel myself starting to charge up a little bit, and I specifically, when I'm doing this show, I don't moisturize, I don't use conditioner on my hair. I will explain why in a second. Hey, that's really good. It's going quite well today. That's pretty. Let's go. That side's not going up too well. Sort of, there we go. And my hair stands up like crazy, and I look like this is completely ridiculous. Actually, this is really good. I'm now going to turn it off without touching anything that might cause the electricity to discharge. And then I just have to sort of sit here a little bit and wait for my hair to drop back down again. Actually, that went really well. That was a really good one. Meow! I touched something that discharged the electricity. Right, so that's charged me up and charged me back down again, so to speak. So and my hair stood on end, didn't it? My hair stands on end. And the reason my hair stands on end is because all those electrons that I piled up, remember, I'm rubbing electrons from the bottom roller onto the band, from the band onto the roller at the top, and then from the roller at the top, it goes onto the ball at the top. And because the bigger the dome you have at the top, the more electrons you can push onto it. Okay, it's literally down to the space. You push too many electrons and they all start flying off. They don't like each other. And that's because electrons repel, because like charges repel. Just like with magnets, if you put two north poles together, they push away from each other. If you take two electrons, which have a negative charge on them, not a positive charge, electrons have a negative charge. If you push the electrons together, they push away from each other. Now, when I was doing that, electrons flying onto my body, all over my body, they've got nowhere to go, they pile up on my head everywhere, and the hairs on my body, ambulance going past, the hairs on my body start to stand on end because they're covered in electrons, and the individual electrons are pushing away from each other, and that makes my hair lift into the air. So you can do stuff like that. The other classic demonstration you can do with this, and I will show you this with this camera here. Let me go to this camera here. Right, because this one is a slightly better one. I'm going to point this at the top of the camera there. Ooh, I'll focus it first. So that's the top of the beast. I've got here a whole load of pie dishes. And if I put them on the top, and I always discharge before I touch this thing. If I put them on top like that, we need a bit more height, and turn it on, electrons will pile up onto the dome. Those pie dishes are metal. This is what happens. Whee! Right.
Marty, we've just lost sound, I think, from you. Hello everyone, I think Marty's just trying to get some sound back, so bear with us just a minute.
How's that? Can you hear me now?
Yep, that's fine.
Yeah,
Marty.
we can hear you.
Okay, that's interesting. I think what's happened is I knocked out my microphone by with the electricity. That's not happened before. Slightly worrying. I'll have to investigate that in a bit. Yes. So, well, okay, but you can hear me now. I'm using a different set of microphones now. So
We can hear you now.
I'm using my earbuds, so the sound isn't quite so nice. Okay, let me just get rid of all these pie dishes first of all. Otherwise, it's remarkable how slippery pie dishes can turn out to be. So, okay, pie dishes. Now the question is, how far back did you see before I lost sound? Where did we get to? Did you see my explanations? Okay, how long have you been in? Okay, so I charged myself up. Let's go to this camera here. We can charge things up and we can create these enormous high voltages. And the voltages can do things. They can make your hair stand on end. They can make things fly about because we are piling electrons onto things and moving them around. Now, this story is not just a story, though, about high voltages. It's also a story about how we tamed electricity. And what I'm going to do now is I'm going to just talk a little bit about that. And I just need to do that now that I've fiddled around with my system. Because, check the time, good. What I want to do now is I want to just talk about, and in answer to Hemblington Primary Eagle class, I will come on to some of those things later. Yeah, when the pie plates flew in the air, we couldn't hear you. Oh, dear, that's a shame. Okay, so the pie plate's flying in the air because electrons repel each other and they just piled up on the plate. Right. So another problem with doing static electricity demos is it kills your kit. Right, so what I want to talk to you about is something very simple, and it's how we tamed electricity and a potato. This is a very simple thing, but it is really important that you understand some of this if you're going to want to understand how electricity really got to where it is in our world. Now, this is a story about two blokes. There's a guy called Alessandro Volta and Luigi Galvani. And Luigi Galvani, I'll come back to that in a second. Luigi Galvani is, they're both Italian. Luigi Galvani in about, let me see, what's the date? It's about 1800. He's messing around in a university in Italy, and he is dissecting a frog, and the frog's leg starts to move, and he freaks out, because frogs' legs don't normally move, because this is a dead frog. And the frog's leg starts to move. So he thinks, oh, what am I going to do? So he messes around and he experiments with it, and he thinks it's to do with the animal electricity. He gets it wrong. And it's Volta that comes along, who's I'd say a colleague. He was actually a competitor in a nearby university, and works out what's going on. He works out that it's chemistry. It's very simple chemistry that uses a battery, that uses a potato to make a battery, because that's what he made. So you take a piece of copper. Galvani was using a copper knife when he dissected his frog. And we're going to attach that to the positive of this thing here, which is a voltmeter. And notice there's a decimal point there, that's important. And then we're going to take a zinc coated nail. And actually the word for zinc coating something is galvanization. Yeah, that's where that comes from. And we're going to insert both of these into my potato like this. And normally, I must admit, I don't normally use a potato. In fact, I've never used a potato. I always use a lemon when I do this, because I think lemons are funnier than potatoes, and they're easier to work with. So we've inserted those in there, and now I attach the positive to my, the negative to the zinc. And there you go, we've got 0.7 volts. So we've created some voltage with just a potato. And that's because there is a chemical reaction. It's an electrochemical cell that we've made between the copper, which is one type of material, it's one element, and the zinc, which is another. And there is some liquid with salts and things inside it. And that creates all you need to make electricity. And we've got electricity flowing, or at least some electricity. Now, the thing is, to prove to you that this is chemistry, if I change the metals around, here is a piece of magnesium ribbon. You might have seen this, you can burn this, it burns very brightly. It's a very reactive metal. If we change the zinc, take the zinc out and replace it with a piece of magnesium ribbon, it has to go in the same hole because magnesium ribbon's quite difficult to insert into a potato, and we attach that there like that, we double the voltage. We go up to 1.6 volts. Now this is more voltage than one of these batteries here, okay? Here's a battery, this is 1.5 volts. That potato is making 1.6 volts, but the potato is making a tiny current, a minuscule current. You would need hundreds and hundreds and hundreds and hundreds of potatoes to make enough current to do anything useful. Now, let me just jump straight to this. Here's the thing, current and voltage are two, I think, of the most difficult concepts to get your head around in physics. I certainly didn't until I started to understand these. If you have an electron, here's an electron, little green ball, and it moves from here to here, okay? From there to there like that, you have moved a current. A current has flowed across the screen. If you have two electrons and you move them across the screen, you've doubled the voltage, okay? Two electrons, double the voltage, one electron, half the voltage. sorry, now I'm getting myself in a tizzle. Rewind that. 1 electron moving is current. 2 electrons moving is double the current. Double the, see, I'm getting confused now. It's all the kerfuzzle with the microphone. Double the electrons, double the current. So what is voltage then? Voltage is how much work you have to do to get the electron from one place to the other place, okay? How much work you have to do. And that is quite difficult to understand. Now, if you had a copper wire running across this screen, the electron could easily travel through the copper wire because the copper wire is really good at letting electrons move through it. It's what we use copper for. It's why we use copper. And it doesn't matter how many electrons move through, it's easy. So the voltage is very, very low. The amount of work you need to do to get the electrons from here to here is almost nothing. If, on the other hand, we have air, you have to use a huge voltage to get the electrons to move across. Now, this comes to a question that people have been asking me in Q&A as to why these high voltages that I'm messing around with are not actually that dangerous. And the reason is because they're very low current. Just like my potato battery, the potato produces a tiny current, but a decent voltage. So with the beast, when you're messing around with that, tiny voltage, 1.5 volts, tiny current. Right, let's go back to this. So when you're looking at the beast, this machine makes a huge voltage, hundreds of thousands of volts, but a tiny, tiny current. Such a small current that it's not going to do any damage to me because it's the current that kills and the volts that jolt. The voltage can set off nerves and things like that and cause pain, but it's not going to do any real damage unless there is current with it. And it's the current you've got to worry about. Right, so let's look at, I'm just thinking we've got a relatively short amount of time now, so I'm going to jump straight to another thing that I wanted to tell you about, that really changed the way we understand electricity, which is this device here. Now this, if I come up there like this, move it back there, it's quite big, I have to get it in shot. This is the world's first, well, I'll show you and then you'll work it out. It's invented by a guy called Michael Faraday, 1821. And what it is, we have a big magnet in the middle, a wire that runs up, down, and to negative here, which I'll attach to a battery. And here's the positive. This is a tray, and we're going to fill the tray with a conducting fluid. And the conducting fluid in this case is salt water, very concentrated salt water. Water is a pretty poor conductor of electricity. And if you add salt, it makes it better. If you add a lot of salt, it makes it actually quite good. And if I attach my battery to this, here's a battery, attach this to there, and all that happens is that, because this is the world's first electric motor, invented by Michael Faraday, 1821. And it sits around this. And it's a very simple thing. And the point, though, is that when you have electricity, you always have a magnetism as well. You always have magnetism. The two are hand in hand together. Here's an even simpler version that's even simpler to understand. Here's a battery. Let's go down a little bit. I've put a big magnet on the bottom. The magnetic field is flowing out and around and back in, okay? But it does that all the way around. And if I then take a copper wire and I attach that to the top and the bottom, and it's a sort of a curled copper wire, I give it a bit of a nudge, there she goes, and it spins around. These are called homopolar motors, okay? They're slightly simpler than the sort of motors you get, but when you have the battery and you have the ability to turn electricity into motion using magnetism, we can really begin to understand how electricity works, and we learn to tame it. Right, I'm very quickly running out of time. Okay, let's have a little look. So what we're going to do now is we're going to jump onto some really big voltages, some really monstrously large voltages. Ooh, no, I'm going to press that button there. Monstrously big voltages, and talk about the electricity that actually you have in your home, because electricity that goes in one direction like that, oh, they've gone blue, it's called direct current, and you don't use direct current, at least not in the mains from your electricity. What you actually use is you use something called alternating current. So the electrons don't move from one place to another. They just jiggle backwards and forwards. They alternate their direction. Okay, so they're not going like that. They're just going, and they do it, depending on where you are in the world, 50 or 60 times a second usually. There's various different standards. Now, it's possible to use this to make a fantastic machine, which I'm going to show you with this camera here. Let me just take this off the table. Invented by a guy called Nikola Tesla. Now, Nikola Tesla comes up with a device. This is it here. Nikola Tesla comes up with, it's called a Tesla coil, and it uses alternating current to do something rather remarkable. I'm going to turn the lights off here, like that. And let's charge up the Tesla coil and see what happens. I have to turn it on at the mains. It's on now. And this is genuinely, this is now we're getting into dangerous territory. Okay, and I'll turn those lights off as well. There, like that. This is quite a dangerous machine because this produces about 1 million volts and actually quite a lot of current. So this you treat with respect. I'm going to put my headphones on. It's monstrously loud. It creates huge sparks, about a foot long, about 30 centimeters long at least. The darker it is, the longer they seem to be. And it creates this enormous spark. Now, the beauty of this is that because this is a digital Tesla coil, I can change the frequency of the sparks. You probably can't hear me because I put my headphones on and I'm using a different set. Microphones. Oh, this is going to be complicated. So it uses, because it creates these sparks that are at a different number of sparks per second. So we started out with a few sparks per second. We go up to 1,000 sparks a second. You can create a change in tone, a change in note. And that means that what I can do is, if and of course, what's better than having one Tesla coil is having 2 Tesla coils. I have a second Tesla coil here. I'm going to try and use both Tesla coils simultaneously to play you a little bit of music. What I need to do is turn that on, and then I retreat to a safe distance with these, which are the controllers. I'm going to get rid of myself because you'll not see the other Tesla coil if I'm there. And we'll start by firing up the Tesla coils and trying to, okay. Right, let's start with, here we go. A little bit of, here we go. Are you ready? 3, 2, 1. Oh, I love these pieces of kit. Okay, that was everything's awesome. Obviously, this one. Let me find you. This one is my favorite though at the moment. This is a. You might recognize this. If you're nerdy enough, you will. Hold on, where are you? There it is. This is actually a Finnish folk song. Honest to God. Right. So there you go, ladies and gentlemen. That is, hold on, bring myself back up. We'll go to this camera here. That is 1 million volts, in fact 2 million volts, because there's 2 of them. The current is actually quite high, which is I retreat to a very safe distance. And that is all I've got time for. I've probably run over already. Let's have a look. Have we got? I'm going to turn the lights on so that we can actually see what's happening and make these safe, because they're not safe until I turn them off, like that. And then let's see, what have we got? So there you go. Hopefully that gave you just a little insight into my crazy world of high voltages. Let me have a look. Amy, I'm going to, have we got time to answer some questions?
Yes, Marty. I think the main one is, how long have you been a scientist? I think is a good question.
Well, I've been a scientist, so this is a good question. A lot of people think that being a scientist means that you're somebody who works in a laboratory. That's not true. Being a scientist, it's you know, you can be all sorts of things and be a scientist. I'm a science communicator. That means I'm a scientist. And I spend my time talking to people about science, which is part of the process of science. So therefore, I'm a scientist. And I've been doing science now, well, since I was at university. I mean, I went to university and did science degree. So that makes me a scientist, I guess, because you're studying science. So you're a scientist. And I did sciences at A level. So that made me a scientist. So I've been doing science since 16, since the audience, the age of most of you guys out there. So that's how long I've been doing science, which makes it more years than I care to work out.
Well, a lifelong scientist, Marty. But what do you think made you want to have a career in science, particularly?
Oh, well, I always liked science. Ever since I was a kid, I sort of was fascinated by science, and you know, all the sort of things that went around it. My grandfather used to buy me all these books about science. These sort of big fat books he would send down from Yorkshire to where I lived in London, and they would be like full of all these amazing things, you know, book about birds, book about inventions, book about history of science. And I would just pour through them as a kid, and I loved that. And we would go to the science museum, and I got into science that way. And then ever since then, I thought, well, this is what I want to do, obviously, because science is really exciting and cool and just fun. And I thought that would be a great thing to be in. And then I went off and did a PhD and did some actual proper research science, laboratory science. And I thought, yeah, this is cool, but it's not for me. I'm actually better at talking about science than I was ever going to be at doing the act of research, because it requires a sort of a very kind of focused mindset, and I'm a bit fickle. I kind of I want to be all over the place, because like this afternoon I've got to go and record a whole load of videos about plant science, which I think is fantastic as well. So I love this, but I also like that. So, and then on Friday we've got a microscopy show, which will be all about mostly about human biology, to be honest. So there's all sorts of stuff going on. Anything else that people have come up with? I know people generally want to know, but somebody's there saying, how am I controlling the music? So the music, the Tesla coils, Tesla coils, you can't buy them, in case anyone asks. That's the other question that often people ask. You have to make them. So I built those. The Tesla coils themselves are controlled with this little doodad here. It's a little control box, and it allows me to do all sorts of clever things. I can just turn the Tesla coil on or off, change the frequency with it, and then I can load in onto the little SIM card that sort of sticks into it, the little memory card. I can load in different tunes, although they're quite difficult to work out. You've got to kind of go in and program the tune properly and then play it. And then I get one for each different Tesla coil, and then they have to be synced up so that they go at the same time. It's very complicated, but basically it's this little magic box here that does all the hard work. And that, by the way, is attached to the Tesla coil, but it's attached by a non-conductive cable. And you might think, how is a cable non-conductive? It's a fiber optic cable. It's just shooting little pulses of light down, because the last thing you want to be doing is attaching yourself by a wire to one of those machines to a thing that you're holding in your hands, because that would kill you, quite frankly. Anything else? I'm just flicking through.
Thank you so much, Marty. I think we're going to have to wrap up so we can start the next one. But thank you so much for joining, and thank you everyone for watching. And we'll see you. We'll look forward to seeing you a bit later in the week again, Marty, for your next session. Thank you so much. Bye, everyone.